Hello. Hello. Hey, Kashvi. Hello.
Yeah, hi.
Hey, so do you see my screen? What's that?
Yeah, I can hear you.
You can see my screen?
Okay, so do you see my screen?
Oh, look.
Yeah, I can see it.
So we seem to be getting a little bit of echo here.
Yeah.
Hmm.
I can try calling you from my laptop instead.
Yeah, try that. Okay. Hey, Kashvi.
Hi. It's not letting me do it on my laptop, so I just called from my phone.
Okay.
Yeah.
Hmm.
It's still.
I know, right? So let's
Huh?
figure this. I'm trying to figure out why is it doing this.
Okay.
So, I'm trying to figure out why it's doing this.
The reason I want to do this sharing my screen is because there's so many different handouts and I want to be able to look at them all. And
Yeah.
The reason I wanted to do this,
so why does it do that? So wait a minute. Um, so you're calling me on your phone? Oh, I
Yeah,
know.
I can turn the
Are you,
volume off from my laptop.
yeah, that's what you gotta do. That's what's going on.
Oh, okay. Yeah. Yeah, I really can't hear anything from my laptop. Just the.
So let's see if we hear my voice twice.
I don't. Cause the sound is lost for them.
Oh, good. Okay, this is just right. Okay, so let's look at all the things you sent me, and you tell me what we need to do here to help you for your test tomorrow. You see all the things that you see the email that you sent me.
Yeah, I see. Okay. Basically, I wanted to start with the review packet because it has everything, and I had questions on a lot of the math and stuff. So I was thinking I could like go through it with you,
Okay.
get your help on the questions I need most help on, and
Okay.
then do the other
That
worksheet.
sounds good. So you
Okay.
lead the way. I pulled up
I
the
don't.
review packet here.
Did I send you the? There's another email. Oh, okay. I don't think I sent you it, but there's a answer sheet one too, so that you can see that,
Oh,
like the answers.
okay. Well, I mean, I really know most answers to these, so you can just talk to me.
Oh, okay. Alright. So basically, I'll just tell you what I think the answer is, and you just go through it like that.
Okay.
Yeah. Alright.
And if it gets to be sometimes actually when people teach physics, they use some different terms, and it's possible there's a term I haven't really heard before, and then we'd want to check your answer sheet just to make sure. There's a few standard terms like the ones about Newton's laws, but other than that, they can be put a little differently by different people.
So do you still have the answer sheet?
Yeah, sure. So email me that so I can open it up if I need to. In fact, I'll open that up on my cell phone so I can look at it while we're both looking at the screen of my tablet. So how have you?
Okay, I'm gonna just find it.
Okay.
It's truly here.
So how have you been doing in physics?
I've been getting 100 and everything so far, but the tests usually throw me off a lot.
Okay.
Yeah. Yeah, because the assignments are fairly easy, so you should get 100 in all of them, but then the tests tend to be a lot harder
Okay.
than the other ones.
You know, most of the physics students that I work with are learning all this stuff in 10th or 11th or 12th grade.
Yeah. Oh, actually, so I just got this right. So, all the math stuff, one of the worksheets is an interpretation of a diagram one.
Uh-huh.
He split the test in half, so we're doing multiple choice, fill in the blank, and interpretation of a diagram.
Okay.
So those are the parts of the review packet we're having a test on.
Okay.
Yeah.
So I have the review packet open, and if you want me to like go to a different part of it, just tell me what we need to look at.
Okay, let me open up mine so I can see. Sorry, 1 second. Okay. So the first page is this, the entire first page, and like the entire concepts questions are something we're gonna do, not the word problem. And then yeah, I think that's it.
Okay. So the things you think you're going to do on the test, why don't you see how well you can answer them for me?
Yeah, but listen, I need to check something really quickly because I think I got something wrong. Yeah, I'm on the call right now. Yeah, so we're not doing any math tomorrow. So all the questions that aren't
Oh, you're not doing the math. Okay. All right.
yeah, but the rest of it is yeah.
So listen, Kashvi, your mom said that we'll set up these. We'll have regular meetings, and so when you get handouts or homework or study packets for the things you're doing in physics, just send them right over to me so I can look at them and see what you're doing, and then
But
we'll meet when we need to.
usually we do them on paper. It's only when I'm studying for tests I have it on
Okay,
file.
but if it's something on paper that you have a lot of trouble with, just take a picture of it and text it over to me.
Okay, yeah. So, okay, we can start the review packet then.
Okay.
on the terms. I don't really have like a good idea on the rest. A couple, and then some of them I'm like really sure on. So I'll just tell you which ones I don't know.
Okay.
So for the first one, I did the push or pull on an object.
Okay.
Yeah, and then for the second one, contact force. I said when an object is in contact with another.
Right. It's the push or pull from one object being in contact with another. So it says units when appropriate. I mean, are you supposed to give the unit for force, which is newtons? Is that when you're supposed to give that?
Give the unit.
Yeah, I mean, are you supposed to mention these units as?
I'm not sure, but I can give them. Yeah, I guess.
Yeah, I mean, anytime it says force, the unit is newton.
So for force, I said, the unit is newton. And then for non-contact force, it's the same thing as force, but without physically pushing or pulling, like gravity, for example.
Yeah, gravity is the best example of that. Yeah.
And then I do not understand force pairs.
So, have you studied Newton's laws? Have you studied Newton's laws? First law, second law, third law?
Yeah.
Okay, Newton's third law is every reaction has an equal and opposite reaction. That's called a force pair. If you're pushing on the wall is also pushing on you. The exact same force.
Yeah, I know the force pairs. I don't know how to I don't know what the exact definition is.
Oh, well, I mean, do you need to give the exact words that someone gave you on a handout, or you just need to describe it in a way that the teacher can tell that you know what it is? Because, I mean, how would you describe force pair? Let me see if I can hear that you understand it.
It's like an object that starts an action and whatever gives the reaction, like the pair of those two things.
Yeah.
Like the two interacting objects.
Yeah. That's called an action-reaction pair. That's another word for force pair.
Is that right?
Yeah, that's right.
Yeah. Then next net force is all the forces acting on an object combined.
Yep, that's right.
And then balance force is when forces in opposite directions are like the same and they cancel out.
Right. That the other way of putting that is that the net force is zero.
Yeah. Okay.
Right.
And then unbalanced forces when the net force is greater than zero, and when the net force is greater than zero.
Yeah, it's better to say not zero, because a net force could also be negative. Because force is a vector; it has a direction. So, if the direction is the opposite direction of whatever you define as positive, then it's negative. So just say it's not zero. It's different than zero.
So basically, like when two forces in opposite directions, one is greater than the other.
Yeah.
That's unbalanced.
Yeah, and also you can go in 2 dimensions and 3 dimensions, have forces in all different directions that you have to sort of see how they total up and balance up. But if they balance and there's no net force, then the object is not accelerating.
And then I said friction. I'll start by defining friction, and then I'll go to each one specifically.
Okay.
Is that fine?
Sure.
Friction is a force that acts on any object or surface like with motion,
Mm-hmm.
like it's like kind of like resisting.
Right.
Is that fun?
Well,
Like,
it's really one surface in contact with another. It doesn't actually have to be moving. Static friction, the surfaces aren't moving, but there's still friction. It's like if you had a pen sitting on your book and you tilted it up a little bit, the pen wouldn't move. You tilt it up a little more, the pen wouldn't move. Tilt it up a lot, the pen would fall right off the book. But when it's not moving yet, that's static friction holding it there.
okay. Yeah, okay. And then the next thing I said was well, yeah. So friction is when two objects in contact with each other, like start motion and like there's like a resistance. That's friction.
Right.
Is that fine?
Yeah, and friction always is in the opposite direction of the motion. If it's moving to the right, friction is a force to the left. It always will want to slow down the object, as we know from friction. That's what friction wants to do.
But and then for static friction, I don't really get what exactly makes it different than just normal friction. Like I didn't really get the type. Like I understand sliding and fluid friction because it's kind of in the name, but I didn't get static friction.
So static friction is if you hold an object against the wall by pushing it, gravity is still pulling down on that object. But why isn't it falling? It's because static friction is pointing in the opposite direction. It's the friction of the wall that wants to keep that object from moving. So it's basically that kind of sliding friction can happen even when the objects aren't moving, because I don't know if I've ever seen sandpaper. If you put two really rough surfaces against each other and push them real hard, they would have a real hard time moving at all. And that's static friction. It's even
Sliding friction because if you're holding it up and you move it around, you're sliding it against it.
right, you're sliding it. But if you hold a book against the wall, the reason it's not falling is because of static friction. If you don't have your hand under it holding it up, you could have your hand on the side of the book with nothing under the book holding it up. And if you draw a diagram, a free body diagram of the forces around that book, the only force pointing up would be the force of static friction, and that's the only reason the book isn't falling. And if you push hard enough, you could keep that book from falling, and it would be static friction keeping it from falling.
Oh, okay.
Okay.
I think I got it. So, I'll just repeat what I got. Static friction resists motion by
Yeah.
like two things in contact.
Yeah, exactly right. It resists any motion at all. And if you put enough force on it, you can get it moving, and then it's sliding friction.
That's flex friction. Oh, okay, I got it.
Right.
And then sliding friction is a force that like resists or opposes the direction
Yes,
of any motion.
exactly right.
You're sliding over.
That's the perfect way to say it.
Okay. Fluid friction is something that like resists the motion of any object in fluid.
Yeah, and fluids.
Yeah.
It's just the same idea as sliding friction, only we're not dealing with solid objects, we're dealing with fluids.
And then next one, gravity. Gravity is an invisible force that it's a force of attraction between objects because of their mass.
Right, that's exactly right.
Okay. Inertia is the idea that anything in motion will continue to be in motion unless stopped by another object or force.
Right. And also, The other part of that, this is Newton's first law, an object that is at rest will tend to stay at rest unless the force acts
Yeah.
upon it to move it. So inertia is anything with mass wants to stay in the kind of motion that's in. If it's moving, it wants to stay moving. If it's still, it wants to stay still until a force comes along to move it.
Got it. Okay. And then mass is the amount of matter in an object, a person or whatever. Weight is a measure of gravity, right?
Yeah, it's the weight is the force that gravity has upon that mass.
Okay. So, yeah, okay. And then momentum is like the force or speed with which something moves.
Yeah, momentum is mass times speed. So it's the it's not exactly a force, but I mean it's defined as mass times velocity. So it is. I can understand using that term force. It is the force that an object moves forward with. Although it's not technically force in the Newton's definition of force, but it is mass times velocity. That's actually probably the best way to describe it. If you have less mass with the same velocity, the momentum's less. If you have the same mass and the velocity is greater, then you have greater momentum.
Okay, got it. The law of conservation of momentum. He gave the definitions of it, but I didn't really understand it.
So say what you remember about it.
Sorry to interrupt, Larry. This is Shweta, Sashi's mom.
Hi.
Hi, how are you?
Good.
So I have a request, Larry, for you.
Sure.
I know we did an hour-long class, but can you please prepare her for tomorrow's test, even if it takes a little bit longer time?
Oh, sure. Yeah. No, I don't have any stopwatch running on. I'll be here as long as your daughter wants to work on this.
Sure. So what I'm thinking is that she prepares and you test her a little bit on this so that she feels confident about the test tomorrow.
Right. Yeah. No, we're talking through every bit of it really well.
Okay, thank you.
Okay. Okay. So you were telling me what you know or remember about conservation of momentum.
It's something about the momentum doesn't change or go anywhere. I don't really understand that.
Yeah. So let me look at a definition of it. If you have two objects, each with their own momentum, and then you total up the momentum, and then they collide with each other, like pool balls in a game of pool. They have a certain momentum. One ball's moved, the cue ball's moving, and hits into another ball, and there's a certain momentum that the two balls have before the collision, and then they both move off in other directions. And if you totaled up the momentum after the collision, it would be just the same as before. That's conservation. Let me see if I can read an actual written out definition and see if it makes sense to you.
Your live stream is getting really blurry.
Let's see what's happening here. It is getting blurry.
Now it's black.
It's black. Oh, so my is it back on now?
Yeah, it's on now.
Yeah. So my screensaver just came on and turned the screen black. So I just had to move it around a little bit. It came back on. All right. So the total momentum of the two objects before the collision is equal to the total momentum of the two objects after the collision. So that's conservation momentum. The total amount of momentum is constant or unchanging regardless of the way that objects collide with each other or move back and forth. you can total up the momentum before an event happens and after an event happens, and the momentums will be the same.
Yeah, I just got the exact definition that he gave. And he said, like, I think it's the same thing, but it's just complicated. The rule that in the absence of outside forces, the total momentum of the objects that interact does not change.
Right.
Which is, oh yeah, that's what you said, right.
Right. So that adds to it the idea conservation of momentum means in the absence of an outside force, you can change the momentum of an object or a system by putting a force on it, and then the momentum can increase. But if there's no outside forces, then the momentum is the same. And that law is the basis of solving a lot of the mathematical problems that you'll do. Maybe you've done some already, and you'll do a lot later, that the way you can figure out the speed of the two blocks after they collide is because of conservation of momentum. You know the momentum before they collided, and so you know the momentum after they collide.
Yeah, I got it. And then centripetal force is a force that acts on anything moving in like a circular motion or around something.
Yeah, it's about circular motion.
Which directs it towards the center.
Right.
Right?
Right. Centripetal force is directed toward the center.
Yeah.
And
circular motion. Sorry. Yeah.
so when you get to drawing free body diagrams about circular motion, we'll talk more about that. But that definition is fine for now.
Circular motion is motion on a curved path, right?
Yeah, I mean, really, motion in a circle, but any curved path, when it's on the curve of that path, will have the same kind of aspects of circular motion. But it really means just what it says: motion in a circle, like merry-go-round going round and round, or an object spinning round and round and round. Most of the rides in an amusement park, a lot of them have circular motion involved.
Newton's first law is an object at rest stays at rest, and an object in motion stays in motion.
Right.
Unless the force acts upon it.
That's perfect. That's were you reading off a piece of paper? Because that's exactly right. That's very good. All right, second law.
The acceleration of something depends on. Wait. I have to check it. The acceleration. No. Wait.
So use Newton's second law is usually just described as F equals ma, force equals mass times acceleration. There's ways to put it in words that make it more complicated, but it's really force equals mass times acceleration.
Let me see what he said. Exactly, because this is complicated.
Yeah, okay. So what did he say?
He said, the acceleration of an object is dependent upon two variables, the net force acting upon the object and the mass of the object.
There you go. And they specifically, the way they interact is that F equals ma. Newton's second law isn't just that acceleration depends on those other two things. It is the way it depends on it is force equals mass times acceleration. And that equation is also the way of solving a lot of the math problems that you come up with in physics. F equals ma. If you have a force of 3 newtons on a 1 kilogram object, it will accelerate at 3 meters per second squared. That sort of problem.
And Newton's third law is for every action there's an equal and opposite reaction.
Yep, that's it. Good.
Can we go over them again at the end?
Sure. You keep an eye on the time. Time doesn't matter to me. It's fine with me to continue this as long as you want. Just keep in mind if you have other stuff to do, you make the decisions on that.
Yeah. Thank you. Perfect. We go grab water.
Sure. Yeah, in fact, I'm going to get some too.
Thank you.
All right. Okay, I'm back. I don't know if you are.
Hello?
Hello? I'm back.
So, that's a concept question.
Okay.
How do you calculate the net force acting on an object? You calculate it by adding all the forces acting on it, and then including, like, the direction in which, most of the forces are.
Right.
The difference between mass, weight, and gravity, mass is the amount of matter,
Mhm.
and weight, and then gravity is the attractive force that acts on everything, and weight is the gravitational force acting on it.
Right. Acting on the mass.
Huh?
Good.
How are mass and inertia related? The more, more mass, more inertia.
That's right. And one of the definitions of inertia is the property that mass has of wanting to stay the way it is. And the more mass, the more inertia. That's good.
What equation relates to net force acting on an object to its acceleration? F equals ma.
Very good. And the F in that does mean net force. The net force equals the mass of the object times its acceleration. And that means that if the net force has a direction, then the acceleration has that same direction.
24. Please slow down.
Sure. It probably takes a couple seconds from when I scroll down to when you see it scroll down.
Oh, yeah, okay, see it now. Newton's law of motion is for every action, there is an equal and opposite reaction.
Yeah, does that make any sense to you?
Yeah, like you said the stuff about the wall.
Yeah, let me show you. I'm going to draw a little picture here. Do you see me drawing?
Yeah.
So here's you pushing on the wall with, let's say, the force you're pushing on the wall will give you a head. And you're pushing on the wall. See my great artistry here? What's the force you're pushing on the wall with? Let's say you're pushing on the wall with 10 newtons of force.
Okay.
Now, the reason why there has to be a action-reaction pair, the wall has to be pushing back on you with 10 newtons, because if it weren't, you would push right through the wall and you would fall into the next room. If the net force is 10 newtons into the wall, then there would have to be some acceleration of you through the wall. It's only the wall pushing back with the same force that allows there to be no acceleration and no motion.
Oh,
Does that make sense?
yeah, that makes sense.
And so you know if something's not moving or not accelerating, there has to be a force that's opposite. Like you'll do some problems with a ball hanging from a string. Well, gravity is pulling down. So if it's not moving, something must be pushing up. The string is pulling up with the same exact force that gravity's pulling down. How do we know it's the same force? Because the ball is not moving.
Okay. Done. Oh yeah, I got it.
Okay.
25.
Okay.
The total amount of momentum when like objects in motion meet each other doesn't change.
Right. From one point in time to another, the total momentum of the system in the absence of a external force, the momentum will always be the same.
Okay. 26. Can you scroll up to the side because I can't see the whole thing?
Yeah, there you go.
Um. I'm not sure about 26.
Okay. It's a trick question because the Earth does come up. By this equation, F equals ma. The force you put on the Earth is equal to the mass of the Earth times acceleration. And the force the Earth puts on you is equal to the mass of you. Well, I guess the golf ball. The mass of the golf ball times acceleration. And the mass of the golf ball is so much tinier than the mass of the Earth. So the mass of the Earth means it's not going to hardly accelerate at all. And the tiny mass of the golf ball means it is going to accelerate a lot. So the Earth does come up to meet you, but it's not even measurable because the Earth is so much more, well, not you, but the golf ball. The Earth is so much more massive than the golf ball that it's beyond the ability for anyone to measure the tiny, tiny, tiny amount that the Earth comes up to meet the golf ball. Plus, if you're standing on the Earth and the Earth came up, 1 millionth of a centimeter, you wouldn't feel it anyway because you're standing on the Earth. You'd have to be outside the Earth golf ball system to detect that each of them is moving. So I don't know if that makes any sense, but it actually does, but it's really not measurable.
So basically, because Earth has a lot greater mass,
Right.
that like the acceleration would be really small.
It'd be really small because the two multiplied together equal the same number. The two forces are equal, but the mass is so much greater, the acceleration has to be so much smaller.
Yeah. Okay. 27. What is the acceleration of an object at terminal velocity? 0.
Good, that's very good. Right. Constant velocity means no acceleration. Terminal velocity. You know what terminal velocity means?
No. This is used a lot.
Yeah, so usually the term for what's the acceleration when an object is at a constant velocity, that can be from any old reason. The car driving down the road at a constant velocity, you walking across the room at a constant velocity. If there's no change in velocity, there's no acceleration. Terminal velocity refers to a falling object, like a skydiver. The faster they go, the more air resistance the air puts on them. So they go faster and faster, and the air pushes up on them more and more and more. And finally, they get to a speed where the force of gravity pulling them down is exactly equal to the force of the air pushing up. And so they no longer have an acceleration. They stay at that velocity. That's terminal velocity means is usually refers to objects falling through the air or through any kind of liquid.
Okay. Oh, sorry, my alarm went off.
Oh, and you don't have to do the numerical problems, is that what you said?
Can you repeat the vocabulary then?
What's that? You want to go back to the vocabulary?
Yeah.
Okay. Here we go. So do you want me to quiz you on vocabulary? All
Can
right.
you get more random?
What?
You do it like a random order?
Yeah, definitely I'll do a random order. If you want me to throw these at you, I will. So tell me about the law of conservation of momentum.
It's basically saying that when two objects meet each other and there is no external force, the amount of momentum will stay the same.
Right. And the amount of momentum will stay the same whether they collide or not. It's from one time to another time there's the same total of momentum, no matter what happens in between, as long as there's no external force. So they don't have to collide, but this is always used in problems where they do collide. So tell me about gravity.
Gravity is the force of attraction due to mass.
Good. That's nicely put. All right. Tell me about net force.
Net force is the combined force applied on an object from all directions.
Good. And what do we mean by balanced? What do we mean by balanced forces?
Balanced forces is when the net force is zero.
Good.
Because two forces in opposite directions that are equal are acting on it.
Good.
So they cancel out.
Good. And how about unbalanced forces?
Unbalanced forces is when the net force is not zero.
Good.
So force is greater in one direction and the object moves that way.
Good. All right. So tell me about momentum. What do I mean by momentum?
Momentum is the force or speed with which something moves.
Yeah, it's really the mass times the velocity. Momentum actually has a direction to it. So, do you know the difference between speed and velocity? Okay. Speed is just yeah, velocity has direction. Speed is just a number. Momentum also has direction, so it's mass times velocity. So however you want to explain it, also throw in there that it is mass times velocity. Okay, so tell me about inertia.
Inertia, the idea that an object at rest stays at rest and an object in motion stays in motion.
Good. And how about centripetal force?
Centripetal force is when an object moving in circular motion, the centripetal force brings it, like, with the force in the middle, or whatever it's moving around.
So let me tell you something about that. Centripetal force is exactly what you said about an object in circular motion. It is the net force toward the center of the circle. Okay, so let's hear about mass.
Mass is the amount of matter an object has.
Good. How about friction and all the different kinds of friction?
Okay. Friction is a resistance to an object in motion. Feels, static friction is when it's restricting an object from moving. And sliding friction is when the force applied is greater. So there's friction between the object and another object that's moving, like sliding. And then fluid friction is the same thing but with a liquid.
Good. All right, so tell me about force.
About what?
Force.
Oh, force is the push or pull on an object.
Good. And tell me about contact and non-contact force.
Contact force is when an object is touching another, and that's the push and pull. And non-contact force is when it's moving it without physically like moving it, like gravity.
Good. Another non-contact force is magnetism. Gravity and magnetism are two, very notable non-contact forces. So what is weight?
What is what?
Weight.
Oh, weight is the amount of gravitational pull in an object.
Good. And how about force pair?
Second action and reaction pair, like in the third law.
Right.
That whatever's acting on it has like equal reaction, and those two things are force pair.
Good. All right, let me scroll up here. So we just have a few at the end here. Oh, so circular motion.
Oh, what is it?
Circular motion.
Oh, circular motion is motion on a curved path.
Okay. Okay, so just tell me Newton's laws, first, second, and third.
Newton's first law is that an object at rest stays at rest, and an object in motion stays at motion, unless another force acts upon it.
Good.
Newton's second law is F equals ma.
Perfect.
Like an acceleration depends on a force applied and the mass of an object.
Good.
And Newton's third law is that with every action there's an equal opposite reaction.
Great. That's great. Well, that sounds really good. Is that all the things? Any of the other things you sent me? Do we need to look at them, or is this really the main part of it? Is to know all these terms and then to be able to answer those questions about the concepts.
There's the diagram.
So, are they in the what you sent me?
Yeah, let me check which. I'm opening up the email I sent you.
Yeah. So I'm gonna pull. That should be coming up on the screen right now.
Yeah, it says Newton's laws SCD and F equals ma document.
Good. Okay. Oh, free body diagram, yeah. So have you drawn many of those, or you just mainly interpret them when you look at them?
Where was it? When did I read it for a second? Oh yeah, we did those, but those were like a couple months ago.
Oh, I see. So do you need to be able to look at this chart and draw the free body diagram? What is this?
Yeah, I think so.
Okay.
Yeah, drawing them, but you won't be able to see them.
Yeah. So,
I guess when you have to scratch it with each one.
you know what I mean. If you want to take a minute, we can go to a different platform that is actually a shared whiteboard that you can draw on and I can see and I can draw and then you can see. Do you want to do that or do you want to do that another time or what?
Yeah, we can do that.
All right, so it's to do drawings of this chart.
Yeah.
Okay. So let me see what I need to do. All right. Hang on. Okay, so we're going to come out of this. We'll keep talking, but I'll switch over to another form for us to work on.
Should I leave it or do you want me to stay on this thing?